Hi 243, this is our last video and we're going to actually do one tiny last little thing with the binomial distribution that I left out of our last video, and then we'll talk briefly about the geometric distribution. So the last thing I wanted to mention for binomial is that we have a way to compute the mean value and the standard deviation for this kind of distribution. So to compute the value for the expected mean, right, the expected value or mean value of the binomial distribution, all we do is we take n, which is the number of trials, and we multiply by p, and remember p is the probability of a successful trial. Okay, and the standard deviation is found by doing a similar calculation, but we do the square root of number of trials times probability of success times 1 minus probability of success. Okay, so let's do a little example here, right? Okay, the computer example we were talking about last time, okay? So if x is still the number of laptops among the 12, right, that we're going to record, then the mean and standard deviation for this binomial distribution of this random variable, right, are found as follows, right? So mu is going to be n is 12, and then p right here, remember p is the probability of success, right? And remember we talked in the last video about how 60% are laptops, right? So probability of success is going to be 60% or 0.6. When I multiply those two things, I get 7.2. Okay? And when I get a standard deviation, I do square root of n times p times 1 minus p. Okay? And so again, interpreting these values means that you would expect, if you did a bunch of recording of 12 customers, that in the long run you would see the expected value would be 7.2 laptops per 12 customers. Okay? All right, so let's think about this slightly differently for a second, and this is when we're going to move into a new distribution, okay? So let's suppose we were not interested in the number of laptops purchased by the next 12 customers, but instead we were interested in which of the next customers would be the first one to purchase a laptop. So these people are walking in the door and you're like, is it going to be that one? Or is it going to be that one? Or is it going to be that one, right? And so this is emphasizing a fundamental difference between a binomial and a geometric distribution. Okay? So how these things differ is that in a binomial distribution, the number of trials is fixed, right? So you're going to say, I'm going to record the next 12 people that come in, and I'm going to check to see how many of them, the probability of how many of them buying a laptop, right? Probability of 6 of them buying a laptop. Alternatively, this question now is asking, how many do I have to use as a trial to get a certain number of successes? Right? So the question is actually like backwards, right? And your book gives a really interesting sort of example. I like the way they think about this, where they say this idea of a geometric distribution, right, not binomial, right? You can kind of think about it as you would be counting the number of boxes of cereal that you have to purchase before finding one with a rare toy in it, right? So instead of saying, I'm going to buy 30 boxes of cereal, what's the probability that there is a toy in there? Now you're saying, okay, how many boxes do I have to buy, right, before I find one that has a toy? So it's a different question. The trial number isn't fixed anymore. Okay, so here's some properties. So there's an experiment consisting of some trials, right, with the following conditions. The trials are independent, right, one doesn't affect the next. Each trial can result in one of two possible outcomes, success or failure, right? You open the box and find a rare toy, or you open the box and you don't. The probability of success is the same for all trials. And so what we have here is a new idea of a random variable. For a geometric random variable, we have x is the number of trials until the first success is observed, right? You have the first success, right? So x could be, 30 if in the cereal box example, you have to open 30 boxes of cereal before you find the rare toy. And by the way, this x value includes the final success trial, right? When you actually open the 30th box and it has the toy in it. The probability distribution of this random variable is called the geometric probability distribution. Okay, and again, we've already sort of talked about a couple of ways that this differs from the binomial. The huge one is that the number of trials isn't fixed any longer. Okay, so let's do an example, and then I think we'll be done for this one. So suppose that 40% of students who drive to campus at your school or university carry jumper cables. I know I do, so I'm in that 40%. Your car has a dead battery and you don't have jumper cables. So you decide to stop students as they are headed to the parking lot and ask them whether they have a pair of jumper cables. Right, so this is a perfect candidate problem for a geometric distribution because notice we're going to be thinking to ourselves here, how many people do I have to ask before somebody says, yeah, I have jumper cables, right? So let's let x equal the number of students that we have to stop before finding one with a pair of jumper cables. This is a geometric random variable, and it'll have a distribution that's geometric. So here is how the rule goes. So just like the binomial had a crazy rule, the geometric also has a crazy rule, right? So if we have a geometric random variable x with a probability of success p for each trial, then our rule, all right, our distribution has a rule or function notation given by this thing right here, right? So probability of x is 1 minus p raised to the x minus 1 times p. Okay, and don't forget x can be 1, 2, 3, 4, 5. And remember, x represents the number of trials that have to be performed before the first success is observed. Okay, so let's try this jumper cable example. So x is the number of students stopped before finding one with a pair of cables. The probability of success here is 0.4. The reason is because we know 40% of students carry jumper cables. So what's the probability that the third student stopped will be the first student to have jumper cables? Again, so think about what this means, right? You ask somebody, they said no. You ask somebody, they said no. You ask somebody, the third person, they said yes, right? What's the probability that it'll be the third person that says, yes, I have jumper cables? So that means we're evaluating this geometric function, right, for a number of 3. We're plugging that in. And so according to the rule, what do we have to do for the geometric distribution? We have to do 1 minus p, that's right here, right? So 1 minus 0.4 is 0.6. And then up here in the exponent, we have to do x minus 1, right? So since x is 3, that means we get a 2 right here, okay? And then here we have to multiply by p. P is 0.4. Okay. We do this, get a little calculation right here, and ta-da, we get this number. So what does that mean, before I go to this next part, right? 0.144 means that the probability the third student has it is 14.4%, right? So now the question is, well, is it better if you asked other people? Is it higher if you ask less people? Or is it a greater probability if you ask more, right? And you might have some intuition about this, but let's try it mathematically, right? What's the probability that 3 or fewer students are stopped before finding one with jumper cables? So in this case, we're actually asking for an inequality, aren't we? But again, we're still dealing with a discrete random variable, which means that we have to say, well, tell me what the probability of the first person, probability of the second person being the 1, probability of the third person being the 1. Okay, so we have to do this calculation here for each of these values of x because we're working with an inequality. When we do that, we get the following right here, okay? And so this is a nice number because the idea is what's the probability you have to ask at most 3 students, right? Okay, that's the idea. What's the probability that 3 or fewer students are stopped before finding one with jumper cables? That's the same question as what's the probability you have to ask at most 3 people, right? And so that says it's 78%, which means that's pretty good, right? Okay, you're going to have a pretty good shot of getting somebody within the first 3 students. All right, we don't have to do that section, so that's the end of 6.7. I have posted a reading for you on our Moodle site, which is an optional reading, and the beginning part of it has some permutation combination stuff which you can ignore, but there is a little section in there on the Poisson distribution, which is a French word, right? And that's purely just for you to look at, just to see what an example of another kind of distribution is. But we're going to be focusing on the normal, standard normal, binomial, and geometric. Thanks for watching.